Welcome this morning, first set of sessions. I have to apologize. I was under the weather last week, and I'm not a morning person, and it's still 6 a.m. for me, and all sorts of things. So apologies if I'm not 100% right now. But welcome to Digital Certificates. Trust is important in any relationship. My name is Jesse Peterson. I'm a CPE at Facebook, and you can find me on Slack and Twitter and stuff in various places, or just find me in the hallway as well. So we're here to talk about digital certificates in trust, of course. And isn't it super cool that I got Facebook.com to show my slide on the front page, just for me? No, that's a complete lie. They did not do that. But how can that be if we've got a little lock icon here and Facebook.com? This is a real browser. And so how can that be? How can my slides be? This clearly isn't Facebook. So how did I do that? I'm going to show you how I did that and how all that works. Yeah, so let's start. Okay. So trust. Trust is huge, of course, all over the place. And maybe you've heard, we've got this crazy thing called the internet. We've got all these devices connected to each other, and they talk to each other. And we've got your laptop and your iPad and your iPhone and your iWatch and everything. And we even let Windows on the network. How crazy is that? And they all talk to each other, and it's really important that they do that securely and that they all kind of trust each other and stuff like that. But the most important player in all of this is, of course, is the end users. Ourselves and the people that we help to use the computing devices and things like that. They need to be in a trusted environment as well. So they know that the sites that they're talking to are who they say they are, and they aren't doing malicious things and stuff like that. And so I'm going to actually pause so I can unmirror or remirror here. Apologies. I don't have my notes. This is up here, right? No, I don't want to mirror. That's better. Okay. Other way around. Where is that button? Does anyone remember? It's like right up here, isn't it? Apologies. There we go. Do you remember how to set the primary screen in Keynote?
Don't mirror. Don't mirror.
Sorry?
Use a separate display.
They're definitely separate. Just my... Oh, we're good. Never mind. I'm completely... Sorry. Like I said, not 100% today. Okay, so we got the internet, we got trust, we got people. I'm hoping to give you an introduction to what certificates are, and hopefully it's not too crazy. So you understand all this, right? It's not a problem? Actually, no, it really is my goal for this not to be scary or intimidating at all. It's really all very straightforward, and I hope that at the end of this, you could hopefully look at all this and it all makes sense. So what do most people think when we think of certificates, right? HTTPS, TLS certificates, of course, are the natural ones. You see these with the little green check marks or text, or the little lock icon I showed you in the beginning, Facebook.com. But there's other things too. There's email, encrypted email, and signed email. Digital signatures is really important. In fact, it's pretty crucial to the way this whole game works. But really, certificates are good for anywhere you need identity and authentication, and anywhere you need encryption and privacy are good candidates for certificates. But to kind of hammer home some of these concepts, I want to talk about how trust has been done in the past. And so you're probably familiar with these types of ways of protecting things or information. And so you've got keys and locks, and we still have them, of course. And the thing that protects a key and a lock is the nature of the key, right? So how it's made pretty much corresponds to the lock that it's made for. It's made to unlock. And so that's for this presentation. Never mind the fact that we could jimmy the lock or force it open or anything like that. We'll just set that aside. But the thing that keeps lock and key protected is the notion that it's secret, right? That the key only opens the lock that it's made for. And that's kind of cool, right? So only the people who have the key can unlock it. But the problem with traditional ways of thinking about locks like this is if you want to share that protection, so if you want to give that box to someone else and have them be able to unlock it, you have to give them the key. And that's not ideal because even never minding the ability to force open locks and things like that, keys are not great because you can lose a key, or it could be stolen or copied, or all sorts of different ways that you can compromise traditional key and lock, a physical key and lock. And the key thing that I want to enforce there is that it's shared, right? So if you want to share this thing, you need to have two keys, right? Or you take that same key and you give it to another person so that they can unlock the device. And that's pretty terrible because you've now increased the chances that something's going to go wrong with that key by sharing it. We have sort of improved a little bit. We took the keys, and instead of them being physical objects, they're now codes or sequences in our heads, which is nice, right? You take the physical aspect out. It's a little bit more portable and things like that. It's also easier to share. In the case of the padlock, it's 3 numbers and a certain way to jigger them back and forth. And oftentimes, combo locks or electronic ones are just 4 digits or whatever. But that's pretty bad too. Because that's not that much information. If that information gets compromised, then boom, someone can get into that lock. It's obviously trivial to copy. The codes are very short, and yet again, they are shared. So if you want someone to be able to access these padlocks or something, you give them the code, and voila. But now you have the shared code with multiple people who have access to the same code that unlocks the thing, which means multiple ways that key can get compromised. Okay, so those are like physical, the padlocks and key locks, those are physical things, but how about the information itself? What if we want to start protecting the data? So there's things called substitution ciphers, and these have been around for thousands of years, and they get complex to very simple. If anyone has ever spoken MacAdmins, that's also, well, you could consider that to be a substitution cipher. But unfortunately, the thing that makes it secret is just the way it works. So if you know how MacAdmins works, it's no longer secret, right? And the same goes with things like ROT13, which is a famous terrible internet encryption, or things like secret decoder rings. It's in some cases like that secret decoder ring there, you can change the key, sort of. You can set the starting position and then the algorithm works differently. But for the most part, that really doesn't matter because you can do frequency analysis and other fancy techniques to get around that. Yeah, so the algorithm or the technique is the key, and when that's known all over the place, you effectively lose your protection, right? So again, it's shared. Multiple people have to know the secret, the way to decode it, and that's terrible. So we're getting a little bit cooler. We've got rotor machines. Sorry, one sec here. Right, okay. It'll be fine. So rotor machines. So these are kind of interesting. They're electromechanical, so they move and they encode the data in super complicated ways that are kind of like substitution ciphers, but they're different in one key way. The algorithm that runs over the data to cipher it is different from the key that you input to cipher it. So what that means is you can essentially change the password, the key, and have it dynamically generate the ciphertext, and it's reversible. And in the case of the Enigma machine here that was used in the World War II, of course, and since the 20s to the 60s, they've been in use for a long time. You can do it in reverse as well. So you can plug in the same key and cipher the text, and you can plug in the same key and put in the ciphertext and get the plain text back out. So this is good. Now we have multiple keys, and once we have multiple keys, we can start doing fancy things like rotating them. Like in the war, they would have a different daily key that they would use. But we're still stuck in the same situation where the secrets are shared, right? So even though they change every day, for example, you still have to coordinate distribution of those secrets out to the people who need them. And that's terrible. We shouldn't have a situation where we have to have all these copies of these secrets all hanging around. So what do? We flip it on its head, and we do public key cryptography. And in the 70s, they were like, hey, we can do better. We have fancy math, and we can do nifty things. And so the way I like to think about it is, back in the beginning when we were talking about physical key locks, if you wanted to share information, you would share the key. But what if somehow you could instead, on the spot, on the fly, manufacture locks, right? So now you only have one key, and you never share it with anyone else but yourself. And instead of distributing a key, what you do is you publicly know someone else's lock, right? So if I wanted to send something to someone else, I would go look up the way in which I need to construct a lock specifically for their key, and then lock that and send the information along. And the only way to unlock that is having the one key, which is pretty cool, I think. This is called the difference between asymmetric and symmetric keys in cryptography. And when you split it out like that, what it effectively means is there are no shared secrets. So people have one secret, and they protect it, and they do not ever share it. And that's really, really central to the PKI thing, because once you start sharing keys, then we're back with the problems that we just talked about. So, so we're improving things here. And so the terminology, a private key is just that. So it's the singular key that is private to the key holder. But it's mathematically paired with a public key. And so there's a one-to-one mapping there. And they really are just that. They're public. So you hand out these public keys, and you're able to have people encrypt data using your public key that only your private key can unlock. Okay, so the shared key way kind of looks like this, although really it kind of looks like this, right? Because there's multiple copies. So you have a lock and you share a bunch of keys, and that's the way that right, things are terrible. It's sort of like twin-engine planes. Sometimes people will say, oh, well, you know, a twin-engine plane is, it's less likely to have engine failure. It's like, no, no, no. A twin-engine plane is twice as likely to have engine failure. There's two engines, right? And so it's the same thing with the shared keys, right? So now you have multiple opportunities for all this bad stuff to happen to the keys when you have a bunch of them hanging out in the world. So instead, we want to move to public key cryptography, where each person has a private key and a public key, and again, there's a mathematical relationship to each one. And what you want to do is, as I was describing, when you want to send somebody something private, you encrypt information to another person's public key. So in this case, Alice wants to send some information to Bob. Alice will take Bob's public key and encrypt the information using that, send it to Bob. Although it doesn't really matter that it gets sent to Bob. Anyone could see it, the encrypted message. Only Bob is going to be able to decrypt it and get the plain text because the public key corresponds to the private key, and only Bob has the private key. So only Bob can see that. And that's the major thing that's really, really cool with public key cryptography is this asymmetric relationship and being able to encrypt things to public keys and decrypt things with private keys. That's the big thing. Just one more analogy is it's kind of like a lockbox. Anyone can put anything into this mailbox, but only someone with the key can actually retrieve it out of, right? There's a compartment where anyone can flip the little lid down and it goes into a secret thing that only the key can unlock. I realize the irony that a physical key here is, but anyway. Okay, the math. The math is really cool. I'm not a mathematician, I'm not a cryptographer, so it all goes right over my head. But basically, there's two large prime numbers and an exponent that is chosen by the key generator. And I just want to review this because when we start looking at the certificates themselves, this stuff actually does show up in the case of RSA. RSA is one type of public key cryptography systems. There are others that are based on, so RSA is based on large primes, and there are others that are based on like elliptic curves and other fancy stuff, math that I don't understand. So the modulus for the prime numbers are included in both the public and private keys. And the RSA key size is actually, in the case of RSA, related directly to the length of the prime numbers. So a 2048-bit RSA key is actually 600 decimal digits of prime numbers. That's what the key size refers to in the case of RSA. So the public and private keys are mathematically derived from these prime numbers and the exponents. You do a bunch of fancy math that includes Greek symbols and stuff that's over my head. But importantly, we'll leave it at that. If you want to know more about this stuff, and it's actually really cool, it's something that I want to learn more about. There's a simplified version of RSA called KID RSA or KRSA, and it basically takes the prime numbers, makes them smaller, and does more simple math than the really, really crazy stuff, and it really walks you through the translations that go on. So definitely go look if you're interested. Fun fact, the RSA was actually invented twice at the same time, which I just find fascinating. So in 1978, at MIT, Shamir, Adelman, and Rivest, thank you, invented RSA, publicly disclosed it and whatnot. But what wasn't known until 1997 was that in 1973, shoot, I don't have my presenter notes, Clifford Cox at the GCHQ, Britain's version of the NSA, also invented the exact same mathematical formulas for this stuff. And they invented them at the same time, different continents, roughly the same decade, which I just find absolutely fascinating. Okay, so because we mentioned key size, I couldn't help myself but to put this in here. This is one of my favorite XK CDs. And it's important to think about for me, I think, because we can talk about all this crazy cryptography stuff and million-bit keys, and it's all really fancy and fun. But at the end of the day, we're trying to help people, right? We're trying to help people be more secure, and the mathematics are really great. They're great tools that we've used, but we kind of have to be a little bit practical about it as well. Okay, so digital signatures are one specific aspect of certificates, and it's actually related to the PKC stuff more than the certificates themselves. But it's really, really critical. The ability to verify the authenticity of a message comes in handy, and you can do really fun things with verifying chains of trust, which we'll take a look at later in the talk. The way, right, so you can guarantee the authenticity, basically the source of information. You can verify the integrity, so you can cryptographically verify that a message was not modified in transit. And non-repudiation, which is basically you can't deny if something was signed by a private key. It's like mathematically impossible. You can't sign something without having access to the private key. So you can't claim, I didn't send that. What are you talking about? You definitely did. You signed it. And it kind of works like this. So Alice wants to send some information to Bob. So she takes the data and runs it through some hashing algorithms, and with her private key, digitally signs a document. And then that travels across the network or whatever. We can cryptographically verify if we have Alice's public key. We can be very, very sure that she signed that piece of data with her private key. Because of the way that the mathematics work with the public-private keys, there's this relationship, and we're very, very sure. I think I skipped, oh right, so this is just the last slide. The digital signatures are a bit different than, it says hashing here on this thing, but it's different than just pure hashing. Hashing is just a one-way function. So if you're familiar with MD5 or SHA-1 or SHA-256 or whatever, those are just one-way functions. Signatures, they actually entangle the signature with the actual data. So there's a relationship to the data and the public key. Whereas a hash is just related to the data. There's no extra part going on. Okay, so with that, let's talk about actual digital certificates. So X509 is the standard that certificates were defined under, and right. So we have this idea of public and private keys and these mathematical relationships and all that good stuff. But we want to be able to use this broadly throughout the internet and be able to send certificates around and encrypt stuff and have it all work across vendors and across countries and people and stuff like that. So we need a very standard way to define it, and it needs to be extremely detailed because the mathematics are quite involved, and it all needs to be codified very, very strictly. And so standard bodies, that's what they're very good at. ITU, in this case, is who picked up this one. The X prefix comes from the ITU's series of standards. They have a whole bunch of lettered standards. The X in this case is networking and communications. I just had to throw in that they also did V32biz, which is really important if you want to frag your enemies better, because 9600K modems just weren't good enough. And once you upgraded to 14.4, you could frag much better. And yeah, so thanks to the ITU, we have better fragging and certificates. So it's also defined in RFCs, a whole bunch of them. The ITU standards are publicly available. RFCs are publicly available. PKCS set of specifications are widely used. X509 is just the certificate part, but there's also private keys and container formats and stuff like that. Those are all defined in PKCS, which were developed by RSA originally, but now they're all open and RFCs and publicly available. And they're all standards, and everyone uses the same formats. Right. So a little history on certificates. So they actually began with LDAP. Way back in the late 80s, X500 was this crazy notion that there would be ubiquitous and ever-present centralized directory services. And one of the problems with the PKI infrastructure is you have to distribute these public keys to everyone so that we can all use them and share them. And so the one way that was envisioned to do that was this X500 standard with all these directory services. So probably familiar with an LDAP server maybe that runs at your company. Imagine that just like bigger and everywhere, and everything's public. So every company, every university, every organization runs their directory service. If not, actually a centralized like global directory as well. And so when you have that, then you can just be like, you can just go look up people, so you can just find their public keys. That's great, right? Because now we can all exchange information securely. And in fact, X509 was going to be the authentication method to access and modify your directory entries. So if like your telephone number changed, you would use your certificate to prove that you were you to your directory system so that you could make modifications and whatnot. However, we don't really have that anymore, and in fact, as MacAdmins, you're probably either already have, are in the process, or are going to be using less directory services on your Macs. Yeah, but history had other plans, so we don't really have directories everywhere, and we have something a little bit different that came up in the 90s that mostly is kind of the way it's done now. So we have these preset bastions of trust called certificate authorities, and we allow our software developers to define. Did we skip a slide here? Sorry. Yeah. Okay. I think we did. That's kind of weird. Okay, so X500, yeah. So we don't actually have the big directory system, so we now have the certificate authority trust system. That's too bad. That was a great slide. I wanted to talk about that. Oh well. Right. So what are certificates? Certificates are just encoded data structures, really. And that crazy poster that I showed you, that's what they look like. And so ASN.1 is the coding standard for how pretty much everything in cryptography is represented as data. They contain a very specific set of fields with very important specific fields, like the public key is kind of a big one, the signature is a big one, subject and issuer DNs, which we'll talk about, expiration dates, all the stuff that you're probably a little bit familiar with certificates. And there's also some optional extensions that certificates can have as well. Certificates are often wrapped in other formats, so PEM files are pretty common. PKC is 12 files or P12, and all sorts of other formats. We'll talk about those in a little bit. But we will focus on PEM for a sec. So PEM is privacy enhanced mail, which is basically a defunct standard now for encoding and encrypting mail. And it came out before MIME and PGP kind of swept the scene. But what it does is at the bottom here, it shows basically what a certificate kind of looks like in PEM format. It's got these 5 dashes and then capital begin, and then the thing that is followed. So in this case, it's a certificate, and then 5 dashes, and then we get base64 encoded text or data. And so base64, you can kind of think of like a substitution cipher, right? You put in data, base64 converts it to a deterministic output based on the input data, and it's reversible, right? It's not really a cipher. It's really meant as a data representation encoding. And the reason why it exists, these PEM files exist, is because things like email have a hard time sending binary data around, so you have to simplify the data into simpler characters by encoding it in base64. And so they're easier to hand around, and they work a little better when you encode them like this. But that's PEM. I wanted to specifically focus on it because they're so common. Okay, so ASN1, I mentioned that. Let's talk about that. So ASN1 is it's very popular. It's everywhere. It's also really complex, and perhaps needlessly so. But it's here now, and it's what we got. It's a generalized data structure, so and you can encode it in a few different ways, although it's pretty standard the way people do it. That's DER encoding. We'll talk about that. And it supports composite types, so you can have lists of things encoded in the binary data, and you can have sets of things, and you can do key value mapping by essentially doing sets, certain types of sets and things like that. So you can kind of think of it like XML or HTML, right, where you have a document, and you've got tags embedded in other tags, and all sorts of different tags and data can be mixed in there. It's kind of like that, but it's a binary format. If you do much programming and have taken a look at Thrift or Google's protobufs, it's similar to that. It's just a binary encoding type of thing. Yeah, and it's got a very specific format. It's everywhere. So it's used in, of course, X500 that we talked about, of which LDAP descended from. Lots of VoIP stuff uses it. Kerberos uses it. If anyone's done SNMP stuff, you're probably familiar with ASN1 and specifically OIDs. That's very ASN1. 3G, 4G, LTE, all that stuff is, all the communication protocols are encoded with ASN1. Yeah, and raw ASN1 with the X509v3 certificates, when you see that binary notation, it's DER encoding. And so you'll see that often around in the literature. So I want to focus on OIDs. They're used a lot. It's basically a hierarchical standard for assigning a number to a concept or a thing. And this helps with binary encoding, right? Because things are easier to represent to computers and numbers than names and things like that. So, and they look like this here. Like I said, if you've done SNMP stuff, you're probably familiar with these. There's these numbers that are separated by periods, and you string them all together. It is hierarchical, so for example, see if I can remember this right, the 1 here represents ISO, which is, ISO is the standards organization, standards body. 3 stands for, I think, the internet, or DARPANET. 6 is the DoD, because the DoD invented the internet, so it all kind of starts there. And then I forget the 1, the 4, and the 1 is, but eventually you get down to 63, which is Apple Corporation's, the OID for Apple Corporation is 1.3.6.1.4.1.63. And it's not just companies, also concepts like the type of encryption or a signature here, SHA-256 signature with RSA encryption is noted as that OID. And so that's pretty common in the certificates. We'll see lots of that. Okay, so hopefully with some of this background, we can actually look at this and kind of get it. So let's see here. Let's start. So this is the whole certificate, and I'll note that in the top left there's the PEM encoding of the certificate, right? So when you decode that base64 text, what you get is the binary data in kind of the left column down the left side here in the various colors. So those are the raw binary values of the ASN1 encoded certificate. And it's just sequences of these fields that are in the certificate. And one of the first ones in this example is the version of the certificate is the first like real bit of data here. They're all version 3, so that's what this one is. The signature identification, in this case, it's a SHA-1 with RSA encryption, which I don't know, if you've done much certificate stuff, you've probably had to replace a whole bunch of certificates in the last year or two because they were all SHA-1 and everyone moved to SHA-2. This is an old certificate. This poster was made a few years ago, which, by the way, I love these posters. They're a great way to explode it. Carl Menner, he actually sells printouts of these if you want to go check them out. No relation. That was part of the stipulation. But they're great. I love them. And yeah, so the SHA-1 indicates the actual signature algorithm that was used to sign the certificate, which shows up later at the bottom of the certificate with the actual signature data down there. And we'll talk more about that in a sec. But all the other standard issue fields are here, such as the expiration dates. Importantly, the distinguished names. So the issuer, I don't think I can make the cursor show up over there, but the issuer and the subject are who these certificates are representing. So in this case, it's an organizational unit called Unit B with a common name of b.com in Ohio. So that's who this certificate is supposed to represent. Whatever the cnb.com is, the common name is what the CN is. And so that's the subject. The issuer, the person who signed the certificate, is above that. And in here it's just called Root. The common name is Root, and the organization is called Roots Inc. Obviously not a real one. but it shows that the issuer is there, and the subject is there. As well, we have the public key of the issuer. So this is the subject with public key, or the subject public key info has information on the subject's public key. So this is a way that we can start establishing trust chains, which we'll talk about a little bit later. And then below that, we've got extension data. So some of the extension data is super critical, and some of it's kind of just informational. In this case, the first extension there is the basic constraints. Pretty much every certificate has this, and it's got information like, is this certificate a certificate authority? So not a CA, as it says up there. So that's false for this particular certificate. And what that means is this certificate is not intended to sign other certificates. It's not intended to be treated like an authority. And when we start talking about certificate chains and certificate authorities a little later, that'll make a little more sense. The authority key identifier is the public key info of the issuer. And this is really critical to again, establishing the trust chains, which we'll take a look at later, because you need to know the public key info of the person who issued the certificate so you can cryptographically verify it. And then the actual signature is at the bottom there that is attached to the certificate, which cryptographically verifies that the certificate was signed by that issuer. This is just one way to look at this information. There's a ton of others. If you've ever used Quick Look on macOS on a certificate, it kind of looks like that on the right. It's the same exact information, it's just presented differently. So the version number is in there, the issuer, the subject, the actual signatures, all that information's in there. Depending on how detailed you need to be, or if you need to extract the information, one view may be better than the other. Obviously, if it's a GUI, it's not amenable to copying and pasting and grepping and stuff like that. But it's all the same information. It's all ASN1 encoded data, and it's all the same. So I wanted to take a little detour and talk about distinguished names. So we talked about the issuer and the subject. In the margins there, it says CDN, and that basically says to go look at this poster. And it's the same thing. It's just more ASN1 encoded values. In this case, we've got the same, the Ohio unit B.com. So this is just more encoding of all of these values. So the United States, the country name is encoded in there, and it has an OID that says that attribute stands for the country name, 2.5.4.6. Same with the state and the organizational unit, which changes, which is organization defined. And then the common name, which in this case, and for most SSL certificates, is a domain name, so b.com. I should note that, again, these are older. These posters are a little bit older, and we no longer depend solely on the common name for DNS matching. We use subject alternative names now, which are additional attributes in the certificate that are used for specifying things like DNS names. So it used to be, oh yeah, what does the common name say? But now it's, no, oh, what does the subject alternative names say? And that can be a list of things. So you can have one certificate that covers many different domain names, whereas you used to only have one common name per certificate. All right, so we talked about PEM, but there are a whole bunch of other things for wrapping and containing certificates. And one of them is PEM that we talked about. DER is the native ASN raw encoded values. There's something called armored PEM, which is for private keys. And this is kind of an OpenSSL invention, which allows you to encrypt the private key on disk. So you can share, well, I wouldn't feel comfortable doing it myself, but you could share an encrypted private key as long as the passphrase, the shared key for your private key is protected, right? So you keep some security around that. PKCS7 is very popular with signatures and signing data and doing things like SCEP and stuff like that. So you can contain certificates inside of PKCS7 structures. P12 are storage specifically for storing certificates and private keys, whereas PKCS7 is kind of an interchange format almost. And then there's other things that you're probably familiar with as well, like if you do Java programming, there's key stores, and those are specific to Java, but they can contain encrypted private keys and certificates. And a keychain on Mac OS is another container for certificates and private keys. And you can encrypt private keys inside of your keychain, right? They're all locked to your password. Right, so there's lots of ways to store certificates, but in the end, at the end of the day, they're all DER encoded. That's all they are. In fact, if we go back to this guy, is it on there? I can't tell. I don't see it. So at the end of this, if you look in OS 10, at the very bottom, there's fingerprints, and they'll usually be SHA-1 or SHA-256, and all that is a SHA-1 hash over the DER encoded bytes. So the certificate is, the fingerprint of the certificate is the certificate, just in a hash function. Okay, so, right. So we talked about public key cryptography. Let's talk about public key infrastructure. So how do we trust? Trust that there's some water. Okay. This is the slide I was talking about earlier that I couldn't find. So there's two, there's more techniques than this, but the two main ones that I think are really cool, and in the case of X509 necessary, are chain of trust versus web of trust. So chain of trust is what we have for browsers and web trust, and pretty much anything that uses X509 is based around this chain of trust model. And so what this basically means is there's a set of certificate authorities that are considered trust anchors. And what that means is you don't need to go to someone else to vet the trust for those certificate authorities. They are inherently trusted. Just full stop, you trust the CAs, and that's all there is to it. It's a yes, no, and you said yes to the set of certificate authorities. Because of the way the chain of trust works and certificate signing, you can verify that any given certificate, if you have all the intermediate certificates, you can verify all the way up to the root trusted trust anchor certificate that certificate came from that root certificate. Cryptographically, you can be very assured of these things. And that's interesting, right? So if you trust a root certificate, then you implicitly trust every single certificate that is generated by that root certificate. And further than that, every single certificate that a CA trusts, you trust every certificate that one trusts. So it's this tree that starts filling out because you trust everything that the CA issues, as well as anything the CA issues, right? So you've got the trust. We'll look at it. The burden of trust here is typically with the software developers, right? So if you've got this list of CAs, how do you make sure, which ones do you include in the list? And the software developers basically solve that for you. So they gather the lists of these CAs, or the CAs go to the software vendors, and they maintain those lists of CAs. Now contrast all that with the web of trust model, which is totally different. So it's decentralized and peer-based. You thought Bitcoin and blockchain was cool. This was cool in 1992. And the way it basically works, and I'm going to be a little hand-wavy here, is you trust your friends, right? So if I know, if Alice knows Bob, Bob trusts Alice trusts Bob's public key, right? So she has his public key, and she's marked it as trusted. Bob has his own set of friends, right? And so through that, you can establish that you trust your friend, and you know that your friend trusts another person's friend. And so what you can actually do is Bob can sign Bob's friend's public key and hand that back to Alice, and through that exchange, you've vetted that Bob's friend is trustable to Alice. And so this web of trust model is kind of interesting because there's no central authorities. There's no single points of failure. It's all this decentralized model. And revoking of trust works the same ways in this decentralized model. This is out there. It does work. It's not really related to X509, OpenPGP or GPG or all of the PGP variants are all based around this model. So I definitely encourage you to look at it because I'm a huge fan of decentralized and pure-based stuff. So it's really cool. All right, so chain of trust. I apologize about this picture. It kind of got cut off at the bottom there. It says root certificate in yellow at the bottom. But this is effectively what the trust chain looks like. And so the root certificate is on the bottom right, and it is the certificate that signs the intermediate certificate, and the intermediate certificate signs the end entity certificate. Now, because each certificate also references the signing certificate's both name and public key, we can cryptographically verify that the end entity certificate, so say your web certificate, the leaf certificate as it's called, because it's like a big tree, the leaves of the tree and the root and the trunk and stuff, is actually issued from our intermediate certificate. And we can do the same thing with the intermediate certificate all the way up to the root certificate. And because we trust the root certificate and all the certificates that its children trust, we have trust, or rather we consider it trusted. The exception, of course, is the root certificate itself, which has an interesting way to tell itself to be trusted, and we call that self-signed. And so when a certificate is self-signed, it's just that. Its own private key signs itself. So if you look at the public key in a self-signed certificate, it corresponds to the same signing signature that was on the certificate. And so you'll see that they have the same issuer and the same subject, because they're the same. And then the other attributes like CA true is typically set because it's self-signed. The point is to issue other certificates. Right, and the public key is the private, corresponds to the private key. You can look at this information slightly differently as well. So here's the trust chain for Facebook.com. It was issued by DigiCert's high assurance intermediate CA, and that was issued from the high assurance root CA. And so the browser knows actually to look at the signatures and verify that, yeah, the dates are okay, it's not expired, it's not revoked, and we trust the root certificate, so this one's a thumbs up. We trust Facebook, right? Yeah, so that's the trust chain. And on macOS, the root certificates are stored in the system roots keychain. And this is just that, just a list of CA certificates. Hope we have enough time left here. That are trusted by the system. So it's just that. It's just a list of root certificates that are trusted. Every operating system has something similar to this. Windows has the certificate store. Linux has these lists, the same thing. They're just files on disk instead of in a container format like Keychain, but they're just lists of CAs. And this is a fun screenshot because it's from a few years ago. And if you know anything about the DigiNotar compromise that happened in 2011, this is kind of concerning, right? So anything that's in that trusted roots thing is implicitly trusted, right? But what happens if one of those trusted things is not so trusted or something happens, like what happened in 2011? So DigiNotar was compromised. The CA was hacked into, and it had issued a whole bunch of invalid certificates, like 600 invalid certificates. But when I say invalid, I don't actually mean invalid because they were completely valid. They were, in fact, implicitly trusted. So every browser trusted that the Google certificate that DigiNotar issued was perfectly fine. And so when you hacked into the CA, you can just do that. You can just say, hey, I'm going to generate a certificate for Google.com or Facebook.com. And because I have this trust on all of these devices all over the world, and I signed it, all of these devices instantly trust that certificate. And because you've hacked in there, you have the private key. You now have the ability to, for anyone who knows to go look at your certificate, you have the ability to spoof those sites. You can pretend like you're google.com or whatever. And that's exactly what happened. So they implicated Iran hackers to spy on Gmail. So they issued all these certificates. And when you're Iran, you have control over the network, right? So if you have a certificate by itself, that's of some value. But if you can redirect network traffic, holy cow, now you've got the whole enchilada. So you can redirect people at your fake server that has your fake certificate that's trusted by everyone, and you can read all their traffic, which is great, right? No, that's terrible. But it happened. So we need to have a concerned eye on these lists of trusted CAs, because they might not always be on the up and up, right? Some things can happen. One of my favorite things about this situation was this was discovered by one of the leaders of the Tor project back when this happened. But this was these are some of the ASN1 attributes that are inside of one of these issued certificates, and they were curious because this domain name didn't exist in DNS. Just like, oh, that's kind of weird. Why would they do that? And it has weird street address. And it turns out that if you translate some of these like street addresses, they're written in Farsi, they're calling cards, they're hacker calling cards that they just embedded in the certificate that an English-speaking person would, probably look right over that, like, oh, it's an address, clearly, because it uses the same, organization and country codes and stuff like that. So anyway, I thought that was kind of fun. Okay, so how do root certificates get into certificate stores? Well, the answer is Apple and Microsoft and Mozilla and Adobe and a whole bunch of other people have these programs for getting root certificates into the operating system. And so these are basically big policy documents that Apple and whoever have written up to specify exactly what a CA has to do and the policies it has to conform to in order for them to be accepted into the operating system, for example. And yeah, so these are the policy documents. In theory, this allows some transparency, so you can also go look at these policy documents and say, yeah, that's a good policy. You still have to trust Apple or Microsoft that they've properly vetted these CAs to be actually in the CA lists. But at least there's some formality around the process. It's not just willy-nilly everyone gets to come in. I think there's some pretty significant fees if you want to be put into any one of these vendors' certificate root stores, like hundreds of thousands of dollars type things. So it's not just anyone can get, and anyone who wants to be on the list gets to be on the list. There's some processes there. But I want to call attention to another type of thing. So we might trust Apple to vet correctly all the CAs in the list. That's great. But what if, and Apple typically will sell you a computer direct, so you have a reasonable expectation that what comes from Apple is from Apple. But what about something like Dell or Lenovo, where they're a middleman, they're a reseller or vendor or whatever, who takes Microsoft's thing, modifies it, right? They put on all their crapware sometimes, a lot of the time, and then they sell you the device. And so that's another element, that's another trust element in the chain. And we could talk a whole bunch about, verifying vendor security and compromising firmware and shipping vulnerabilities and stuff like that. But at least in this specific case, it's worth noting that this has also been abused in the past. So Lenovo shipped malware, which is pretty terrible in itself. But part of the way that malware worked was it added a certificate to the root store on the machines that was able to be compromised. And in Dell's case, it was even better. So Dell shipped computers with a trusted certificate as the CA in the trust store. So anyone trusted that CA. But what they did was they included the private key too. So now you have a bunch of Dell computers out in the wild for which the private key is widely known So if you can construct a certificate and sign it with that private key, all of these Dell computers trust it, which is terrible. But that's the way it happened. Okay, so yeah, so we've got trust. What if we don't want trust anymore? What if we're like, okay, someone screwed up, now we need to revoke trust? There's a bunch of technologies to do that. The most simple is CRLs, certificate revocation lists. These are just literally a list of certificates that are bad. And the certificate authorities will publish these. A lot of times certificates get revoked for not nefarious reasons. So like it had the wrong street address. So you revoke the old certificate and you issue a new one. That happens all the time. So sometimes the CRLs get very long if you're actually doing the administrative CRL stuff. Online Certificate Status Protocol, OCSP, is an in-the-moment check of whether the certificate is good. So you can go query the certificate authority and say, I have the certificate, is it good? And it'll give you a thumbs up or thumbs down. OCSP stapling is kind of a new thing where you include the OCSP response in the web request itself, and it has a very short time span window. So you can be reasonably sure that as long as everyone's clock is synchronized, which is a reasonable assumption, that this certificate is good as of half an hour ago or whenever it was last checked and stapled. However, the problem with OCSP is if you have control of the network, for example, and you're able to modify traffic and stuff, you can just block OCSP and be like, nope, sorry, you don't get to do that. And most browsers, even if they are doing OCSP checking, most of them aren't, they'll just fail open, right? So, oh, I can't verify the certificate? That's cool. We'll just let you through. Don't worry about it. So if you're a hacker in between and you don't want, you can just block OCSP. So they invented must staple, which requires that something have an OCSP staple, so you actually can't avoid it. So even if a website has OCSP stapling, and then it suddenly doesn't, that's a situation in which you don't trust that website anymore, and so that's what must staple is. There's also out-of-band browser blocking, so Chrome and Firefox both have an ability to push out block sets very, very quickly that don't require like software updates, and so this is kind of like XProtect on macOS. And the purpose is basically, if another DigiNotar happened, how do we very quickly just ban all of those very, very quickly? And so that's what these are. What about, let's try and get better at trust, right? So we've got this whole bunch of implicit trust stuff, and we want to try and get better at it. There's some new technologies. One of them is called certificate transparency. And what this is a certificate authority will publish all of the certificates that it issues, every single one. So you can go to one of their certificate transparency lists, and you can see exactly which certificates they are publishing. And this is useful in a few different ways. So for example, if you buy your certificate from Entrust, and you see that out of the blue, DigiCert issued a certificate for a domain you own, that's concerning. Wouldn't you want to know that? So you can go look at those, compare them, and make sure no one's doing anything nasty. So improving transparency is always a great thing. There's another thing called CAA, or Certificate Authority Authorization. Kind of similar, it specifies in DNS which CAs are allowed to issue certs. So basically tightening down the things that these trusted CAs that are in these very vaulted positions, what they're able to do and how they're able to act. So they're not so implicitly trusted. But one way that we can get much better at trust is lowering the issuance windows. So if a certificate is valid for a year, that's a long time, and a lot can happen in a year. So what happens if instead we only issued certificates for a few days? That's much better, because what happens is then you have to do a continual renewal of those certificates in order to consider them renewed. And so the nice thing about that is, let's say some website goes rogue, and we need to stop trusting it now. One way to do that in the current system is to go revoke those certificates. So go publish information about those certificates that are now bad. Or in the case of very, very low issuance dates, what you can do is just stop trusting it. So if it's down to a window of days, If you just stop trusting the certificate going forward, then people will naturally just start blocking them, right? Because their expiration date will be passed. So that's one way to solve it the other way. I think it's a more reliable system because you don't have to worry about these things. And when we were talking about OCSP stapling, it's effectively the same thing, anything, right? If you're going to be talking to your CA and cryptographically verifying that you are still a good standing certificate, why not just get the renewal, get an actual certificate and lower the window down to a few days. Okay, so that was trust. The computer, the device is preloaded with a list of trusted certificate authorities. And there's some problems with that. These things are implicitly trusted. And so just be a little bit conscious of that. One thing that's, that you can do, and there's a bunch of different ways to do this, so I won't go into it too much, is basically think about vetting your list of CAs. So have your security software actually list out all of the trusted certificates and make sure they are the actual correct ones that you want to do. No one's accidentally slipped a bad one in there that's going to fool your users or anything like that. So that's something to put on the list of things to do. Okay. In the very beginning, I showed you I successfully spoofed Facebook.com, and I want to show you how to do that because it's really not that hard. All right, but in order to do that, we're going to actually create certificates. And so to do that, we need a few things. And I'm down to 10 minutes, so I'm going to go through this super duper quick. We need some certificate attributes, company name, blah, 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 street address. You of course need the public key to insert into the certificate, and of course the private key to sign it. If you're doing a typical thing, like for a web certificate, you generate the private keys. You create a CSR, which is the document that has the attributes in it that you want to give to the CA that they will sign and generate your certificate. Unless you're self-signing, in which case, oh, nice incomplete slide, isn't that cool? Unless you're self-signing, in which case you don't hand it off to a certificate authority, you just self-sign. If you're the CA, the way it works is you receive that CSR. You don't forget to take the money because that's important, and certificates cost a lot of money, especially their EV certificates. Those are pricey. So certificate attributes, public keys, et cetera, in the CSR, and they'll fabricate a new certificate. Sometimes they'll use the attributes that you put in your certificate, and sometimes they'll just cherry pick a few of them, like the common name, and just leave the rest of them. That's pretty common, especially for just plain Jane SSL certificates. And then they'll sign that certificate and deliver it back to you. In this way, you have the private key. Right, so there's a separation of the private key, never goes to the CA. You keep the private key for you because it's private. And then you just send the attributes with a digital signature to the certificate authority, and they will sign it and hand it back. So now you have a certificate with a private key without ever having to send the private key to anybody. You keep that local, so that's particularly important. So I wanted to show you some of this stuff, and let's give that a go. So I'm going to remirror here. All right. I imagine that's pretty small. Okay. Is that okay? Can you see? All right. So I am going to go to my desktop here. I'm going to make a directory. So the OpenSSL tool is super duper cool and does everything crypto. Everything under the sun, and and one of the things that it can do, of course, is generate private keys. And there's a subcommand to genRSA, and that's all you need to do actually is just hit genRSA, and it will actually spit out a private key. This is a real RSA private key. But it's kind of useless just being printed out here. Oh, and by the way, don't do this at a presentation with any actual private key because it's no longer private. All you guys just saw my private key. Luckily, it's just a temporary one that we generate on the spot. Yeah, it's not a big deal, but don't show your private keys to a bunch of people. That's terrible. Right. So what we want to do though is actually save this private key out so we can use it. One way to do that is with the switches. So we can go dash out my key.key. So now that same private, it's actually not the same private key, it generated a new one. So now that private key is in the file, so we can use it. And I wanted to show you, OpenSSL can do ASN1 parsing. So when we take a look at the ASN structure, so this is the PEM encoded structure, of course. Here we can take it, so this is the ASN1 dump of that private key. And the sequence is, it's pretty boring in this one. It's just a list of integers. And it doesn't really tell you what the integers are. They're literally just integers. That's all a private key is. And this is the raw ASN1 value, printout. But there's another way to look at it. OpenSSL, almost all the commands have the ability to take a look at keys, and you can have it just print out the same thing. So all it did here was read in my key and then print it back out. But we don't want that. That's pretty useless, so I'm going to hit no out. But it didn't print anything, right? So what do we want? It just hid the output. What we want to do is have it print out the textual output instead of the PEM format. So if you put a dash text on it, it will actually print it out. So this is a little better. It's the same integers, but it's helped us by putting some helpful information. So here's the modulus. This is the modulus goes in the private and the public key. Here's our public exponent. So you'll see these two values in almost everywhere that this private key is used, because that's how the PKI stuff works. There's a whole bunch of other stuff too for like the specific primes that are involved, the exponents, the coefficient, all the crazy math stuff. But this is a nice way to look at the structure of those files. Okay, so I'm running out of time here. So what we want to do is now create a CSR. So the REQ OpenSSL keyword is a way to do that. So let's see here. I think it's in key. I had these all noted, but then I had to restart. No. Oh, you want to go dash new. Okay, I think that's all I need. So what it's going to do is going to ask me some of these attributes that we need, right? So we're just going to fill in here. We're going to do the US country code. I already screwed up. So US country code. For the common name, we're going to put in www.facebook.com. So here's our certificate request. This is the CSR file. Because I forgot to specify the dash out, let's just do that. Yeah, cert.csr. Yeah, thank you. Don't put a challenge password, it just encodes it as an attribute. It doesn't actually protect anything. So now we have a CSR file here. We can ASN1 parse this just as before. And here we go. So here's actual attributes in the ASN1 format. The ASN1 also has an indent feature, which will actually show you the structure of the ASN1, which is pretty cool. Okay. But what we want to do here is actually create a self-signed certificate. So these are the attributes that will be submitted up to the CSR. But in the case of a self-signed certificate, you don't want to submit to a CSR. You want to sign it yourself. So we're going to do that with the X509 thing. That's just a special switch in the REQ method of OpenSSL. And yeah, okay, so US. It didn't save my cert. Oh, actually it did. Right, so if we, yeah, okay. So this is now a certificate. It's no longer, if we scroll up here, it begins certificate request. So it's now a certificate. When I append the -X509 switch, it turns it into a certificate. And just as well, it's got ASN1 attributes. The OpenSSL X509 command will examine these. So here's Here's my modulus again. Here's the attributes, www.facebook.com. And in that file, if I look at this, I'm going to actually just rename it to PEM. Use PEM, because I didn't think to do that. So here's my certificate that I just generated. Now, how do we get it to show up for Facebook as a trusted thing? And I know I've got 52 seconds left, so we're going to be super quick. And the answer is we just put it in the keychain. I've already got the fake one that I fooled you guys with so brilliantly before in there, so I'm just going to delete that. And all you have to do, now that this is in my keychain, all you have to do is trust it. Always trust. So that's it. So all you have to do is import it into your keychain and trust it. And this is the same for any operating system. The reason why I was able to do this for Facebook.com is because it was just my computer. I have control over my own certificate authority in my computer. So I just overrode the trust and said that, you know what, this certificate is fine. It's perfectly fine. Even though it has Facebook.com in there, I have explicitly trusted it, and it's fine. So then at that point, all I would have to do, and there's 2 seconds left, is configure my web server to use that certificate and then visit the website. And then it's done. I don't think I had very many slides left, if any, but I'll just quickly see. Oh yeah, there's some automated issuance options like SCEP and DCE-RPC. Go see Tim Perfett's talk, I think on Friday. But otherwise, thank you.